Let's walk through the problems on this practice for the test. So the first problem here, you were told you'll flip 3 coins. If all the coins land heads up or all the coins land tails up, you win $10. Otherwise, you lose $4. So what is the expected value of the game? Or if you play 80 times, what do you expect to win or lose? So the probability of all heads is 1/2 times 1/2 times 1/2. So that would be 1 over 8. And you can imagine the tree diagram, which would have 3 levels, one for each coin. And only one of the branches would be heads, heads, heads. Similarly, one of the branches would be tails, 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 which means that that would also have a probability of 1/8. So together, 1/8 plus 1/8 gives us an overall probability of 1/4 that all 3 coins will land same side up. If you play 80 times, therefore, your best prediction is that you'll win 20 or 1/4 of those times, which means you'll win $200, and you'll lose the other 60, which means you'll lose 60 times 4, 240. You are predicted, therefore, to lose $40 if you play 80 times, or you want to look at it this way, 50 cents per game. What you would need to do in order for this to be a quote-unquote fair game, which is to say that you would expect over time to neither win nor lose money. So that means that over time you would expect to net $0. You would have to win $12 each time that all the coins landed heads up. 20 times 12 would give us 240 instead of 200, and that would make up for the 240 you lose the other 60 games. Okay. When it rains, number 2, a tree diagram. When it rains, you get a ride to school, but when it's nice, you walk. When you walk, you have a 60% probability of arriving late. When you get a ride, you have a 30% probability of arriving late. There's a 30% chance of rain tomorrow. So to construct the tree diagram, we're going to put rain, no rain on the first level, and we're told that there's a 30% chance of rain. And we then said there's a 60%, there's a 30% probability that if it rains, you will be late, which means there's a 70% probability that you will be on time. If it doesn't rain, there's a 60% probability that you'll be late and a 40% probability that you will be on time. When we multiply down, we get these 4 values here, and these all add up to 1 because they represent all 4 of the possibilities. Rain late, rain on time, no rain late, no rain on time. So now to calculate these probabilities, the probability that you are late to school, we have to sum these 2 probabilities here, 0.09 plus 0.42, giving us 0.51. Here, the probability that you arrive on time given that it rains. So we're saying we're looking only at the situation where it rains, and we're trying to figure out what's the probability that you will arrive on time. And that is really just this conditional probability right here, the 0.7. Or if you wanted to do it a different way, you could say it's 0.21 times over 0.21 plus 0.09, which is again just the 0.7. When we do it this way, the probability that it rains given that you arrive on time, now we have to look at these 2 outcomes here, the 0.21 and the 0.28. When we add those together, we get our denominator of 0.49, and the numerator will be the 0.21, which means that we'll get 0.21 over 0.49, which is equal to 0.43. So that's the probability that if you arrived on time, there was rain. The probability that it rains or you arrive late means you have to look at all the probabilities that involve rain or late. So it means that you have the 0.09, the 0.21, and the 0.42, which gives us a total of 0.72, or you could say it's everything except the 0.28. Okay. Tree diagram number 2, when you study, you have a 0.75 probability of getting an A on a science test, 0.25 chance, it should say, of getting a lower grade. When you do not study, you have a 0.3 probability of getting an A and therefore a 0.7 probability of getting a lower grade. Overall, you have a 0.57 probability of getting an A, and you have a you have a 0.45 probability of studying and getting an A. So here's how we start to fill this out. So we had the 0.75, the 0.25, the 0.3, the 0.7. We had the 0.45. We know the overall probability of getting an A is 0.57, so that means that this 0.45 plus this had to be 0.57, so that makes this have to be 0.12. We also knew that this probability here times the 0.75 had to equal 0.45, so to figure out this probability up here, we would divide 0.45 by 0.75 and get 0.6. Well, once we have that 0.6, we can just subtract it from 1 to get this probability here of 0.4. And then going down here, we can divide the 0.12 by the 0.4, giving us 0.3 here. And that means we would have to get 1 minus that, or 0.7 here. So now for these probabilities, the probability that given that you got an A, you studied, well, that would be of the two probabilities where you got an A, 0.45 plus 0.12, that would be your denominator, numerator 0.45, so that means that it's 0.79. And that means that if you ended up with an A, there was a 79% chance it was a result of you studying. The probability that you study or get an A would be everything except this 0.28, or 0.45 plus 0.15 plus 0.12. The probability that you do not study and do not get an A is this probability down here, 0.04 times 0.7, the 0.28. Now, again, when you're figuring out the probabilities with ands, you're multiplying these two probabilities together. Okay, then we were asked to construct a two-way table. We put study, not study as column headings. We put A, not A as the row headings. We have our totals here. And so the probabilities in the inner boxes here are the four probabilities down here. Study, get an A. Not study, get an A. Study, do not get an A. Do not study, do not get an A. And then we just summed them across the rows and down the columns. And what you can see is that we end up with the probability here, the 0.6 and the 0.4 are these two probabilities up here. These two don't show up explicitly in our tree diagram, but they're equal to the 0.45 up here plus the 0.12 and the 0.15 plus the 0.28. Okay, so this team had an overall record of 14-6. They played 8 of those games without their point guard, and in those games they were 5-3. That means that in the games where they did play with this point guard, they won 9, which is 14 minus 5, and they lost 3. And so the question, are the events winning and losing and playing with or without Courtney independent or dependent? That means, in other words, do they have an influence on each other? Does the playing with Courtney have an influence on whether or not you win? And the way that we can tell that is by looking at the probability of winning with Courtney versus the probability of winning without. Those two differ. And so it's clear that these are dependent events because we know more about whether the team is going to win if we know Courtney is playing. And we can tell that based on the fact that the probability of winning with Courtney is different than the probability of winning without Courtney. Okay, here we have a Venn diagram, and we have 70 students represented here, and that would be 18 plus 11 plus 24 plus 17. The students who play a sport are in this circle here, and that would be a total of 29 students. The students who are in the choir are in this circle here, and that would be a total of 35. The students who do neither are here, and that would be 17. The 11 here represent the students who both play a sport and are in the choir. So we can answer these questions. How many students play a school sport? It would be 18 plus 11, or 29. How many students play a school sport or are a member of the school choir? Would be the three numbers here summed, 18 plus 11 plus 24, which would give us 53. Everybody out of the 70 except for these 17. How many students play a sport and are a member of the school choir? That would be just the overlap here, or the 11. How many students are not a member of the school choir would be everybody outside the choir circle, and that would be the 35 students. Um, and let's see. So that's actually what that should say. That should say 35, not 46. And then for E, name two ways to determine how many students play a sport. We could either add these two together, or we could add these two together and subtract from 70. Both of those would give us the same value of 29. And then a two-way table here, the inquire and play sport would be the overlap. Inquire but not play sport would be these 24 people here. Play a sport but not inquire would be these 18 people here, and the neither would be these 17 people here. And so then we get a sum of all who play the sport, all who do not play the sport, all who are in the choir, all who are not in the choir. Okay. The sample space is the list of possible outcomes for a given set of events. So when we roll two dice and find the sum, the only possible outcomes are 2, 3, up through 12. And these are not equally probable because there are many more ways to roll a 7 than there are to roll a 2 or a 12. There's only one way to get a 2, one way to get a 12, and there are 6 ways to get a 7. So they don't all have the same probability. Flipping 3 coins and counting how many of the coins land heads up. The different outcomes for that would be 3 heads, 2 heads, 1 head, 0. Notice we did not say, what are the outcomes of how all 3 coins landed. We just said count the number of heads. So the only possible outcomes are 3, 2, 1, 0, and these are not all equally probable. There's only one way to get 3 heads, but there are 3 ways to get 2 heads or 1 head, and there's only one way to get 0 heads. So the 0 heads and 3 heads are more unlikely to happen than 2 heads or 1 head. In number 8, you're asked to calculate a number of probabilities. And in the first one, you were asked to figure out the probability that you'll pull out a pair of socks if you pull 2 socks without replacement from a drawer containing 5 red, 4 blue, or 3 green, and 3 green. So you could pull out either 2 red, 2 blue, or 2 green, so you have to figure out the probabilities of each one of those and then add those 3 together. So the probability of pulling out 2 red would be 5/12 times 4/11, because after you pull out the first red sock, there would be 4 left out of 11, and that gives us 20 over 132. Probability of 2 blue would be 4 times 3, 4/12 over 3/11, and 2 green would be 3/12 times 2/11. And so when we add together all 3 of these, we end up with 20 plus 12 plus 6, which is equal to 38 over 132, or 0.288. For the next one, you're told that this class has 12 seniors, 12 juniors, and a teacher picks 5 students at random, he says, to participate in a field trip. All 5 turn out to be seniors. The teacher claims, well, that's not so improbable. There's a 20% chance of that happening. So we're going to provide evidence that the teacher's incorrect. So the probability that you would pick 5 seniors without replacement would be 12 over 24 times 11 over 23 times 10 over 22 times 9 over 21 times 8 over 20. When we work all that out, what you end up with is 0.016, 95,040 over 5,829,120, or about 1.6%. So the teacher is certainly not correct about that, and something is fishy. Okay, next one, we're told that the whole square contains 200 randomly scattered dots. And so you're asked to estimate the probability that if you select one dot from the square, it will be located inside the circle. So since the dots are randomly scattered, the proportion of the dots that will be inside the circle is same as the proportion of the area circle to the area of the square. So when we do that calculation, we find that, and so we can pick any unit we want for the area of the square. That doesn't change anything. So we're going to say, just for ease of calculation, suppose the square is 2 units by 2 units. for an area of 4 square units. The circle then would have a radius equal to 1 unit, which means that its area would be pi r squared, or pi times 1 squared, so it would be equal just to pi. So the ratio of the circle to the square would be 3.416 over 4, and that equals to 0.7854, which means that the area of the circle is 78.54% of the area of the square. Well, when we multiply 200 times 0.7854, we end up with 157.08. And so the probability that we would pick a dot in the that would be in the circle is 0.7854. The number of dots that we could estimate would be in the circle is 157.08. And there are actually 159 inside the circle, so our estimate is pretty close. Okay, and we have a test for performance-enhancing drugs, which is 98% accurate in detecting the presence of the drugs if an athlete has taken them, 95% accurate in returning a negative result for those athletes who have not taken PEDs. So based on previous research, it's believed that 5% of athletes have taken PEDs. So what is the probability that an athlete who receives a positive result has taken PEDs? So again, we set up our tree where we have 0.95 who have not taken PEDs, 0.05 who have. If you have not taken PEDs, your probability of testing negative is 0.95, probability of testing positive is 0.05. So we do these calculations. And if you have taken PEDs, your probability of testing positive is 0.98. So when we do these calculations, we end up with these 4 different groups: the true negatives, the false positives, the true, this should say false negative, and these are the true positives. So we want to figure out of all the positives, what proportion of them are true positives. So we add up all the positives, which would be the 0.0475 plus the 0.049. That's our denominator here, and our numerator is the 0.049, which is just the true positives, and that gives us 0.508. So what we're saying is that if you are one of the positives, you have a 0.508 probability of being in the PED group. And so if you test positive, it's still only a 50% probability or so that you actually took PEDs. Okay, if we retested everyone, and I know this is the trickiest part of this, what would be the probability that if you receive a positive test, you took PEDs? Well, what we would do is we would take the positives who were false positives, and when we retest those, they would test positive at a rate again of 0.05. The true positives, so that would be for false positives. The true positives, the 0.049, would test positive again at a rate of 0.98, because these probabilities here don't change. The probability that if you have not taken PEDs that you test negative or positive, and the probability that if you have taken PEDs you test negative or positive, these probabilities stay the same. So when we test this group, again, we're going to get the 0.05 times the 0.0475, and when we test these people again, we're going to have 0.98 times the 0.049. And when we get those two values, we get 0.04802 and 0.002375. So we again put these true positives over the sum of the true positives and the false positives. And this time we get a value of 0.956, which means that on the second testing, the retesting, there's a 95.6 probability that if you test positive twice now, you have in fact taken a PED. Now, if in fact our research had shown that it wasn't 5% but 15% of athletes that had taken PEDs, how would the answer to our question up here change? And so it would be that the true positives would now be 0.15 times 0.98. So the true positives, this number here would be 0.15 times 0.98 to find the true positives. And the false positives would be now, instead of 0.95, would be 0.85, and that would be multiplied by 0.05. When we do that, we get 0.147 and 0.0425 this time. And so the calculation would be 0.147 divided by 0.147 plus 0.0425, which is now equal to 0.776. So the probability goes up when there's a higher percentage of athletes who have taken PEDs.